Hi, everyone. My name is Paul Stack. I'm one of the engineering managers at Pulumi, and thank you for joining our joint webinar this evening with our friends from Spot. And this evening, we're actually going to talk about provisioning, managing, and scaling Kubernetes clusters across any cloud with Pulumi and Spot. With me, I have Amit from the Spot team, and I'd like to hand over to Amit so that he can actually talk to you about Spot.
Hi, everyone. Good evening or good morning, depending on where you are. My name is Amit. I'm a product architect for Spot by NetApp, dealing with containers specifically with the product we're going to talk about, which is called Ocean. Today, our agenda is going to be the following. We're going to have an overview or an introduction to what is Spot by NetApp, a Pulumi introduction. We're going to see how we can actually use Pulumi to deploy Spot resources. We'll have a live demo, and we'll have some time for questions and answers. So let the fun begin. Starting with Spot by NetApp, a little bit of background before or in order to set everything clear. So most cloud providers today provide three purchasing models for their cloud compute. There is on-demand, which is you pay as you actually consume. It's usually quite expensive. And that's the main barrier for it. The second option that you can actually use is reserved capacity, where you can actually make commitments for, usually it's 1 to 3 years. You can pay upfront, fully upfront, no upfront, partially upfront. It really depends. And it will provide the discount of something between 28 to 72%, depending on the payment method and the longevity of the commitment. It's much less flexible. It requires a lot more planning. And you could always need to maintain and make sure that you have enough commitments in order to actually cover your consumption in the cloud and have discounts for all of those. And the third model, in order for the cloud provider to be able to provide both the on-demand and reserved capacity, they usually have very, very large data centers. So in order to make sure that those resources that they're running are not going to be underutilized, they offer the access capacity option, which is usually called Spot instances, Spot VMs, or something alike. The idea is that you get the same machines for up to 90% less, but there is no guarantee for availability, meaning the cloud provider can take those machines away with a very short notice. So in AWS, it's going to be 2 minutes. In Azure and GCP, it's going to be 30 seconds. And the idea is that you need to have some sort of a mechanism to make sure that your application is not going to suffer from it. Let's start with talking about why Spot. So Spot was founded by DevOps engineers who had firsthand experience with expanding cloud deployments. They saw how quickly it can lead to escalating cost and complexity. So for that, we actually developed a cloud optimization platform that allows the customer or allows you to make the most out of your cloud deployment. We provide automated optimization of your cloud infrastructure. We do it in different ways. So the first way is to continuously optimize your cloud compute. We have AI-driven provisioning identifies and deploys the ideal mix of compute, machine life cycles. So it's going to be using both spots, commitments, and on-demands, and in the best mix possible in order to make sure that your costs are going to be the least as possible, in order to make sure you utilize the cloud in a good way. The workloads or the infrastructure will be driven by the workloads, meaning we will make sure that you won't have waste, or you'll have the minimal waste as possible in terms of the capacity needed to run your applications. And we also ensure infrastructure availability by using predictive algorithms that utilize the actual cloud models, the access capacity in the best possible way, making sure that whenever there will be an interruption, we will preventively replace the machines. If there will be no other access capacity, we'll fall back to on-demand. We'll constantly make sure that your application is up and running and available. How do we help our customers? So the first thing is we reduce the cost of infrastructure. This is one big barrier that a lot of organizations run into while using the cloud, it's going to be by up to 80%. And we actually do that by utilizing the various compute types, the various life cycles that are possible, and we do it automatically based on what's currently available in the environment. So we'll constantly optimize your infrastructure accordingly. The second thing is that we reduce the infrastructure operation burden dramatically. So we do that by automatically provisioning the compute resources, and our application-driven auto-scaling features allow that as well. And also, we simplify and accelerate your cloud application delivery. So we make things much simpler for containers and Kubernetes, and we also provide SLA for the usage of your infrastructure. So at the end of the day, you'll be able to utilize excess capacity backed with SLA, making sure that you have the availability for the best cost, for the best price possible. We're trusted by over 1,500 customers from different segments, different sizes across the globe. So you can probably relate to some of the names. A little bit about our portfolio. We have products in three main areas: cloud cost visibility, where you can see Cloud Analyzer. We have infrastructure optimization, where you can actually see the DevOps space, where we help you optimize your applications in terms of the infrastructure behind the scenes. And we have the commitment management, which is eco specifically, where we manage your commitment plans based on the actual consumption of what you're using. And another important thing, we support the three major cloud providers, which are AWS, GCP, and Azure. A customer can easily connect to our console, register a new Spot organization. Inside this organization, they can connect or create multiple Spot accounts, and each account can be connected to either an AWS account, a GCP project, or an Azure subscription, which allows you to have some sort of an hybrid cloud platform that from there you can actually manage the infrastructure of your workloads in those three major cloud providers. The way that we actually do our automation is based on cross-account IAM roles. You have to give us permissions on your accounts. Based on those permissions, you will be able to create resources on top of our platform, and according to the configurations that you will specify, our platform will allocate and launch the correct infrastructure to suit your application needs. The product that we're going to focus on today is actually Ocean. Ocean is our product for containerized workloads. So Ocean is an automated data plane for the cloud. It actually works mostly with Kubernetes. It also works with ECS. So we can actually connect to your control plane, which can vary from various different types of Kubernetes and containers orchestration platforms. The way that we actually integrate with your cluster is with a single controller pod that runs inside the cluster. This controller pod will fetch the relevant configurations of the various Kubernetes resources that you're running on top of your cluster, and it will report it back to our SaaS platform. Our SaaS platform will be responsible for making sure to allocate the right and most efficient infrastructure to accommodate your workloads, requirements, and constraints according to what's specified. So by that, you get container-driven autoscaling. So what we will actually do, we'll inspect all the requirements, which are the requests for CPU, memory, and GPUs. We'll see the constraints that are specified, node selectors, affinity, anti-affinity, taints and tolerations, and anything else that is specified on the deployment level. And based on that, we will make sure that we allocate the right infrastructure to accommodate your workload's needs. So you can actually define from the container side of things. Like you can say that this specific pod has to run on on-demand instances, and Ocean will accommodate that accordingly. The second feature that you get is cost showback. What we do is we actually calculate the entire pricing of the cluster, and we break it down to the various different namespaces and applications that you're running on top of it, so you can actually easily understand what's the pricing that is associated with each one of your applications, and show back to your organizations, be able to charge back those. The third thing is container right-sizing. So we actually monitor the actual utilization of each one of your pods versus the requested resources. And based on up to 2 weeks of data, we actually give you a recommendation on how you should set your application requests. this can allow you to dramatically optimize your application requests and reduce the dramatic waste that could have happened otherwise. At least from my experience, a lot of developers that are the ones that work on the applications usually guess what should be the resources for their applications, and this could be a very, very useful feature in order to make sure it's optimized. And all of those things are actually backed by our algorithms and AI-driven infrastructure deployment methods. So we're actually using the various life cycles of instances, and we're using multiple machine types, sizes, availability zones, and life cycles all the time to make sure that things are as optimized as possible. And on that note, I'm going to pass the torch to you, Paul, to introduce Pulumi.
There's some great questions here regarding the content. If you want to answer them in flow before we transfer,
I'm gonna reply on chat.
Answer them all. Perfect. Okay, so as Amit talked about, everything that where this intersects with this infrastructure. Okay, so now we're going to talk to you about Pulumi, because Pulumi is an infrastructure as code tool, and we're not saying it's infrastructure as code. We like to term it as modern infrastructure as code. Now, what that actually means for us is that we can start to bring in familiar programming languages and tooling that include your linting tools, your testing tools, your security tools, interacting with your CI/CD workflows, all of these different pieces to give you a nice workflow for creating and managing your infrastructure. And because it's using these modern infrastructures, these familiar programming languages, and it gives us the ability that we can start to create integrations with any cloud and using a nice architecture pattern that suits the use case that you can actually do. So Pulumi is actually a free CLI. It's an open source CLI and an open source plugin model for all of the providers. But in storing its state, Pulumi has the ability to use self-managed backends, which are free, or of course you can pay for a commercial SaaS, which gives you much higher guarantee of maintaining your state levels as you go through. I'm hoping that today I can show you an alternative way to infrastructure as code, because there are a lot of players and a lot of tools in this ecosystem right now, but showing you the integrations like we have with companies like Spot, means it could give you a new way of thinking about how things work. So Pulumi works with your favorite tools and your favorite platforms and your favorite languages. Okay, so we support all of the major cloud providers. Let me rephrase that. We support what are classed as the leading cloud providers in some areas. So AWS, Azure, Google Cloud, DigitalOcean, et cetera, in multiple languages. So the Node.js based languages, so Node.js, JavaScript, TypeScript, Go. It has the .NET Core based languages, so C#, F#, and VB, and of course Python. Okay, and because it is a CLI tool, it integrates very well into your normal CI/CD workflow. So all interactions with all of your CI tools, and of course then it allows you to interact with different SaaS providers like Okta, or different network providers like Cloudflare, and so on and so forth. So it brings you this mix and matched experience around these different areas. So what has been working in Pulumi like recently? Like, what are the new developments that we're trying to bring to the infrastructure as code space? So the first thing that we've been working hard on is that basically CLI is not the be all and end all for lots of people these days, and lots of people are starting to think programmatically about code. So what they don't want to do is have a manual interaction with the CLI, and they want to drive their infrastructure through an actual application. So the automation API gives us the ability to do that. It's like a strongly typed API that sits across the top of our CLI, which means that you can start to bring in infrastructure workflows as well as other code that has to happen within that application. One of the coolest use cases I've actually seen that is somebody actually deploying infrastructure as from a Python app, and building a nice little application so that they have a self-service web application for people to choose VPCs or virtual machines or any of these different things. We've started giving people the ability to create multi-language components. So you would define your infrastructure module in one language, And as it is then schematized, we can auto-generate all of the other SDK languages that Pulumi supports as part of it, which means a nice workflow for the individual types of users within your organization. Excuse me. And then lastly, we've been working very hard to deliver what we class as our best-in-class support for our native providers. And these native providers are building on top of cloud abstractions. So like we have an Azure native, which is built on top of the Azure REST API specs. We have AWS native, which we announced last week in preview, which sits on top of Cloud Control API. And we have Google native, which is built on top of the Google Discovery API. So we're working very hard to be able to deliver features for our users faster. Why familiar languages? We often hear people ask us this question, like, why not Mark? Why not DSLs? Why not different things? So we can give the ability to users to have the productive tools that they use today. So they use their IDs, they use their IntelliSense, their auto-completion. Of course, if you're a Python developer and you're able to write infrastructure in the Python language, then you have so much access to training materials, online communities to help you lots of different things, because the Pulumi SDK is just an SDK. It's a declarative SDK that sits on top of an API. Of course, then it also gives you the ability to have your package managers to create your reusable libraries and your components. And then you can start to, as you get more experience in infrastructure as code and start to learn new tools and techniques, you can start to unit test and integration test your frameworks. You can start to introduce your code coverage, your static analysis. And of course, this entire thing drives towards more reliable and more secure infrastructure as code. And then you can even layer in items like policies to stop things happening within your organization, to turn on security groups that are open to the world. You can actually have tests that run as part of your CI pipeline that stop that from happening. So to get started with Pulumi, there's kind of, we're looking at the code on the left, there's kind of like three pieces of makeup to a Pulumi application, okay? So we have the imports, which are effectively the libraries that come in. So Pulumi is our core library that gives you access to all of the internals of Pulumi itself. You would then have AWS, for example, as an SDK library, and then you would have extensions. In this case, it's AWS X, which sit on top of the AWS language, or excuse me, on top of the AWS package. You would declare your resources. Resources are usually of types relating to pieces of the individual infrastructure that you're creating. So in this case, you'll see an S3 bucket. In the demo, you'll see a Kubernetes cluster, and then you'll see a Spot ocean, and a virtual node group and different things. And then, of course, you can export parameters back so that users actually get feedback from the different pieces of the system. So a Pulumi project is the top level item. A Pulumi project has a program. A program has a number of stacks to it. A stack is a representation of configuration and state. And of course, inside your program, you have a list of resources which have inputs and outputs. So that's the anatomy of a Pulumi application and Pulumi works. Our use cases are usually around infrastructure and containers and serverless. And we're actually able to interact with all the clouds to be able to give you a nice developer workflow around this. I'm not like picking developers rather than operators. I'm actually saying it's a very productive workflow as you actually write it. So we're going to go straight into today's demo, and we're actually going to look at some code around these different areas. So let me share my screen. And just to make it clear, I have pushed the code to a repository in the Pulumi org. So it's Azure AKS with Spot Ocean. And you can actually follow along, and you can take this for a test drive yourself, because everything I show here is open source and free, except for the accounts that you would have to enter. So let's have a look at my Pulumi application. My Pulumi application is kind of based in two pieces. It has an infrastructure setup, and it has an application setup. And the reason I've tended to break this apart, in fact, let me just make that a little easier for people to see. There we go. And it kind of denotes the potential separation within your organization itself. Okay, so you may have a operations team who manage your infrastructure, and you may have developers who have to deploy applications into your infrastructure. We're not always in the situation where a single team can be involved with both. So a Pulumi application kind of has a pulumi.yaml file, which has a name, it has a runtime, it has our package.json file, which has all of the dependencies in it. This is in TypeScript today, but of course, everything I'm showing you can be easily transferred into one of our other components. We have our node modules. We have a tsconfig because we're in TypeScript and we're showing best practices. And then lastly, we have an index.ts file. And an index.ts file is kind of where we do all of our configuration and the loading of all of the components that. So I'm going to take you through this, and then we can actually run this. And I'm just going to let the application run in the background while we're actually talking about this. So Pulumi is a CLI. If I run the command Pulumi, it will give me all of the items, and it tells me to begin working. Use Pulumi new for templates. The most common commands are Pulumi up, Pulumi stack, Pulumi config, Pulumi destroy. But what I'm actually going to do is I'm going to create a new stack, and Pulumi stack init will ask me, and it's like, what do you want the name of your stack to be? And today we're going to call it Spot Demo. And it's created the stack. And now we want to create some configuration to go with that stack. So the provider that we are actually interacting with today is called Azure Native. And we are going to say Pulumi config set Azure Native and the location. And the location will be West US. I want to create my Kubernetes clusters in Azure in the West US data center. So we can set that configuration back. And what Pulumi will do now is Pulumi will give me a graph of what it's actually trying to do. It's going to declaratively tell me the actions that it's going to create as part of the setup here. So the first thing it tells me is that it's going to create a Pulumi stack. Okay, so that's that top level representation of the configuration and state. And you can have many stacks that sit alongside each other, okay? Because a stack is a representation of the outputs and inputs of a program as well as the configuration that needs to drive them. So as long as a stack is named independently from each other, then you can actually allow that to happen. Then we're going to create like some random names. We're going to create a private key. We're going to create an Azure resource group. We're going to create an Azure Kubernetes cluster. We're going to then use the output of the Kubernetes cluster to be able to interact with Kubernetes itself. We're going to deploy a Spot controller, which we'll look at in a second, and that has secrets and config maps and cluster roles and jobs and deployments and all these different things and cluster role bindings. And then the last two pieces is that we're going to deploy a Spot Azure Ocean and an Ocean virtual node group. So Pulumi's telling me that it's actually going to create all these different items, and I can even have a look at the details of how everything is actually made. So we're just going to say yes, and then I'm going to go back and look at the code and make sure everything is as expected. So my fingers are crossed that this will actually work, but if not, we'll make our way through. So as we can see, we're trying to be a little declarative here, and Pulumi has it tries to follow the idea where a resource is made, a constructor of a resource is made of a name, some optional arguments, and some optional options, okay? We'll talk about the options a little later because those are a little more sophisticated to what we actually need to worry about now. But we can see that we're going to create an Azure resource group that will be called Demo AKS. So Pulumi uses auto naming, okay? So because there are a lot of resources in the cloud that you cannot call the resource the same name, so like an S3 bucket or a resource group or a storage account, Pulumi tries to employ auto naming by default. So what that actually allows you to potentially do is to create, you can change your infrastructure in a more highly available way. So you would create a new resource group before you destroy the old one. Traditionally, in infrastructure as code, by changing the name of a resource, it would just destroy the resource and bring a new resource into its place. But in this case, we're actually trying to do it the opposite way. This resource group will just have a list of tags. Tags is an option within our SDK, and you can actually see I've stepped into the code so we can actually see what's going on in the code. And I can even get my IntelliSense. I can say managed by, and we can have a managed by argument, and we can even have, what else is in here? Location. By default, we've set the location across everything, but we can make a location that's completely separate from each other. After this, we're going to create a SSH key. This SSH key will be used to allow us to SSH into the cluster nodes in our Kubernetes cluster if we really want to, but we're not. It's just to satisfy what the API actually requires here. So now we're going to create the managed cluster. The managed cluster will sit inside this resource group, and Pulumi has what we've actually done here is we've said we've intrinsically linked the cluster to the resource group using the .name, which means Pulumi understands that it needs to create the resource group first before it creates the managed cluster. We don't have to specify these relationships. Pulumi will understand these relationships for us. As part of our Spot setup today, what we actually need is we only need a managed cluster with a single Kubernetes agent pool. Okay, so it's just, you can see that it's just one node in the cluster, and it's an agent pool, and it's of size DS2 v2. It has a DNS prefix, which is just demo AKS. It's going to deploy Kubernetes version 121.1. And what we want to do is we want to enable this cluster as an Azure CNI-based cluster, not a Kubernetes cluster. And Amit can talk about a little that later. That's not a requirement, but that makes integration with Spot a little easier. And then lastly, of course, we want to be able to SSH into the cluster if we really want to. And then what we can do is we can actually start to interact with the cluster, and we can say, hey, now that the cluster has created, I want to be able to get the credentials for that cluster. So I can pass in the resource group name, and I can pass in the cluster name, and I can get the resources in this. And this is using a little bit of a more advanced technique in Pulumi, where it's called Pulumi All, and it's using applies. And what this is effectively doing is it's resolving promises. It's telling Pulumi to resolve this promise at runtime so that I can use this. And then basically from the resolution of that promise, I can get the value of the kube config, and I can get base 64 decoded because Azure sends it back in base 64 encoded. And then I can dynamically inject this kube config into what we call a provider. A provider will allow us to strongly type the resources that we want to interact with. So when you create a Kubernetes provider, by default, it will try and use an ambient kube config environment variable that sits on your local machine. But here we're actually strongly typing it, and we're saying, hey, I want you to interact with the Kubernetes cluster that we have just created above using the credentials that you've actually done. And we can see that I'm able to pull that detail back. Okay. So we've written a little custom code here. This is some of the awesome stuff that that Amit told you about, where you have to deploy a controller onto your Kubernetes cluster that will allow Spot to interact with it. Okay, so and we're taking advantage again of some very cool Pulumi ways of working here, where we've created a component resource. If you think of this as a package that has just not been packaged and pushed to a location, this component resource will take a list of some arguments and some options, and it will also return some details when it's actually resolved. So the thing that we do is inside this controller, we will read the Spotinst token, we will read the Spotinst account, we will create a Kubernetes secret, which has these Spotinst token and account. We will create a config map. That config map has anything around the cluster identifier for the controller that we need to pass in, and we will create a service account and a very long cluster role that is all documented, that says it's read-only here, that these portions, it has draining ability, it has cleanup ability, it has CSR ability, and so on and so forth. You can continue seeing it. But the most interesting thing is we will bind that role to our cluster, and then we will create a deployment, and that deployment will pull a specific container that is actually the Spotinst Kubernetes cluster controller. Of course, This is demo code. We would have to extend this so that we would take the ability to take an image name and an image version, and that we would have to have different liveness checks or whatever you need to do. But this is very much like prescribed about how you would deploy this into your cluster. And then lastly, after we have the deployment running, we have a job which will run as part of the cluster as well. Amit will give a little more detail around this very shortly. After we have the Spot controller, and notice I've been able to use the options here, where I've basically been able to say this Spot controller depends on the Kubernetes provider and the cluster, so that both of these options, or excuse me, both of these resources are fully resolved before I start to create the Spot controller. And then after the Spot controller has been created, we can create the Ocean, the Azure Ocean in Spot, which we pass in some of the outputs of the controller so that we can link these two together. And then lastly, we can create an Ocean virtual node group of a specific size. So there's like in 100 lines of code, we actually have deployed all of the pieces of infrastructure that go together to make up this, this setup. And then what I can do is I can actually see that there have been 16 resources created in 4 minutes. And I can actually, Pulumi stack output, and we're going to just keep that kube config so that we can interact with some things. And then lastly, export. I want to create my kube config locally so that now I can actually kubectl, get nodes, and I can actually see that there is a node available inside my Kubernetes cluster. And you can see it's AKS agent pool. And just to go back to my code, just to show it's the same one, we have a name called agent pool. So everything is up and running. We have an agent that's available. It's 5 minutes old, and we can actually start to see what's going on in here. So we can see that the kube system has been created. So if I flick across to the Spot console right now, and you can see earlier there was no clusters to show, and I refresh this, we should see a Spot cluster. I'm hopeful. There we go. So we can see the creation time was 1831, so 5 minutes ago in West US, and it's Ocean AKA. That's fine. We can see the Kubernetes version, and we can see all the different pieces of it. There are currently no nodes because it hasn't needed to scale up, but there is a virtual node group available for it. So what I can do is let's pretend that this is an existing piece of infrastructure that is available within your organization, and we want to deploy some applications into it. Okay, so I've written some other code that deploys some applications. Okay, so first thing I do is that I'm going to create a namespace. Okay, so that we can actually inspect. If I go back to in my namespaces, you will see that there is no namespace called Hello World, but I want to be able to show you that we actually create this namespace and we can have a look at what's going on inside this namespace. We're going to create a deployment. Now, this is using our Pulumi Kubernetes provider, and this Kubernetes provider actually maps to the API spec of Kubernetes. So we keep up to date with that open API spec, and we're about 15 to 30 minutes behind the deployment of a new version of Kubernetes. So it is as up to date as it possibly needs to be. Okay, so I am going to remove this resources section for a second, and I'm going to say I want to create a deployment. That deployment needs to sit inside this namespace I have created. It will just have a single application, and it's just going to deploy an Nginx application. It's not going to do anything special. And I'm going to comment this one out so that we can come back to this part of the demo a little later. And I'm going to swap across. So I have created my kube config, and we can actually kubectl. I can get my namespaces, and we can see it's the same namespaces. Just to show you. And they're very close in time. So it's exactly the same cluster. So what I'm going to do is I'm going to run the command Pulumi up here. And Pulumi up is going to use that provider that has been, or that kube config that has been injected. And I'm actually going to Pulumi stack init demo application. I'm going to create a new application. So if I run Pulumi up, I was testing this demo earlier. I apologize for that. We can see it's going to create a new stack, and it's going to create a namespace and a deployment inside that namespace. I can deploy this, and it should be very fast to actually deploy this because it's just an Nginx container and a namespace. I promise you it'll finish shortly. There we go, deployment complete. And now if I get my namespaces, we will see a new namespace that starts with hello world. And if I kubectl get pods, namespace is hello world. We will see that there is actually a pod available, and it has one replica running. Now we can even go back to Spot here, and we can see that we now have a namespace. Let's refresh this. And we can see that we have a hello world namespace, and we have the deployment inside it, and it's running a single pod, and we can actually want to scale this pod a little more. Okay, we want to increase the memory request that this pod actually serves. And what we're going to do is we're going to run Pulumi up. And what Pulumi will do here in this time is it's actually going to see that there is a change to the spec of the application. The application will be, the change in the spec will be to change the resource request as part of the container. But in this time, what's actually going to happen is that we can see Spot is actually going to scale out. Amit, do you want to talk through the scale inside of it here? What it's doing on the hood?
Yeah, so definitely. What will happen now is the deployment will be updated. We'll see a new pod being created. So Paul, you can just trigger a kubectl get pods for the namespace. We'll see that the pod is reaching a pending state because currently there is not enough capacity in the cluster. We need 6 gigabytes of memory, which we don't have. The single node that is existing in the cluster do not have that. So what will actually happen is that the Ocean controller will send the information of the pending pod to our SaaS platform. It will recognize its requirement, and then our SaaS platform will actually review the various different configurations that are needed, and it will launch a new machine to the cluster to make sure that this machine will accommodate this specific pod requirements, and then the pod will be able to be scheduled. So in about 2 minutes, we'll have the pod already being created and scheduled on top of the cluster. Paul, you should probably click the refresh button on the top right.
There we go. We have a new node.
So you can already see that a node is being created, and soon this node will be registered to the cluster and will be ready to go.
I didn't actually notice that refresh button at the top right on it, so thank you for that. And of course, what Amit's saying, because this pod is classed in a pending mode, we can actually see Pulumi is still trying to schedule the deployment of this application. And this actually reflects exactly what you see in the UI right here. And there we go. So in this case, we now have a node. I believe this is
not ready yet. It will be ready soon. Still kicking off.
Yeah, and we can now see that there is a node in the virtual node group that is happening in here. And that node is currently initializing.
You can click on the error. It's just going to be removed. It's a UI error. Yeah, and go to the Nodes tab, refresh it again. Let's see what happens.
Not quite yet.
Not yet.
This is happening in the US, so it's a little slow for me, usually. But we can still see that the Pulumi is waited for the deployment to happen, and we can still see in our pod listing that the pod is still pending, so it's still scheduling. Really thinking hard about this. I think it's quite a large node it's actually trying to schedule here.
We'll get there.
So while that's happening in the background, the other way that we can actually do this, so this is based on resource constraints and different pieces. Amit was actually able to show me yesterday that not only that, but you can include a node selector and you can actually push these applications onto nodes of a specific type. So in this case, it will spin up a new DS2 V2 node, and it will actually deploy an application onto a specific node type or whatever selector that you actually need as part of this code. And I'm hopeful that this will soon be there. VM status is healthy, so it's trying to now schedule all the right pieces as part of the cluster.
This is the demo code, intervene.
It's okay. It's actually working because we can see that the status is healthy and it's just trying to do the last of the Kubernetes pieces. And if I now kubectl get nodes, we can still see that we've only got one agent pool that's happening. So this is actually happening as part of Spot, not happening directly as part of Kubernetes. So this is where Spot is actually managing this on your behalf. Just really thinking hard about this. We can leave this in the background, Amit, if you want to demo what this would look like in a production setup.
Yeah, sure, I'll do that.
I will stop sharing and give you back the screen.
Thank
you.
Okay,
it's all yours.
So before moving on to demonstrating how Ocean looks like in a production environment, just a little bit about the AKS Ocean onboarding process. So Paul showed that as code, but just a little bit explanation behind the scenes. The first thing we need to do is we need to install the controller. There's another part that only happens for AKS, which is running the AKS connector job. Technically, what happens behind the scene is we're fetching some of the configurations of the nodes from the cluster itself. And only after doing that, we'll be able to actually create the Ocean cluster. So this is the actual process that happened. For Kubernetes users specifically, we also need to manipulate the managed service identity to give us some other permissions in order to manipulate something else to make sure that the nodes were registered to the cluster. And I'm going to share my screen. All right. You should be able to see my screen now. So this is a live Ocean cluster, and what I want to emphasize on is several things. First of all, you can see the number of nodes that are being managed currently. You can see the total saved amount, the potential cost, which is how much you would have paid if you ran this on demand, what do you actually pay, what you pay for the Spot, and what are the savings, which is the subtraction between the two. You can see the savings, the percentage of savings. One very important thing we can see here is the actual resource allocation. So we get to a point where both the CPU and memory are allocated in a very, very highly manner. So we have 90% of CPU and 85% of memory. This is dramatically high and hard to achieve while trying to allocate the infrastructure on your own, especially for a cluster that constantly moves and like the application increase in terms of size and decrease and so on. So this is happening continuously. Another very useful feature we have is called Headroom. Headroom is a way for you to keep a little bit of extra capacity on top of the cluster. So Headroom can be configured either automatically or manually. So you can specify it in percentage out of the cluster, for example. In this case, it's specified to be 10%. And our backend actually calculates the most common deployments in your cluster. And based on that, it allocates units of Headroom across the cluster to make sure once your applications will scale up, it will be able to rapidly schedule without the need to wait for the instance to launch and register to the cluster, as we saw in the demo, that sometimes it takes a longer period. So this actually assists with those scenarios. You can see the pod activity, and another thing I want to emphasize on is the distribution. So what you can see here is that we actually utilize multiple different types and sizes of machines. In this case, it's only running in one specific availability zone, but it could run in several different. So you can see that we're utilizing multiple spot markets. A spot market is a combination of an availability zone and a machine type. There's two reasons for it. One of them is to make sure that this could happen, the high allocation. The second thing, it actually helps us utilize the spot markets better in a way that will prevent interruptions and make sure that your infrastructure will be more stable, because the probability of losing multiple different types of machines at the same time is lower. So we want to make sure that things are distributed and we utilize the spot markets in a very, very good manner. We can also utilize multiple life cycles. In this specific cluster, it's not the case. We only use spots because they are currently available. And the customer doesn't have reservations or savings plans that we can utilize. Some other things I wanted to show. So the log is quite interesting because you can actually see scaling events in the log. So you will be able to see information about both scale ups and scale down, why we made the decisions that we actually made. So in about a few seconds, it will be loaded. So we can see the log here, and you can see for each scaling event, you can see the information of what triggered that, and you can click the View Details button. In the View Details, you can see the pre-scale and post-scale CPU and memory. You can see the pending pods and the missing headroom units that caused this scaling event. So this is the case here. You can see the restrictions, you can see the requests, and you can also see the machines that we launched in order to accommodate those requirements. For scale down event, you'll actually see a simulation that we run behind the scenes to verify that all the pods that are running on top of the nodes that we're going to terminate can be scheduled on different nodes in the cluster. So this is what you can see here. Two more things I wanted to show. One of them is the cost analysis. So the cost analysis actually allows me to see in a namespace view, what am I paying for each one of my applications in terms of compute and storage costs. So you can actually understand how much you're paying for each one of the applications, and you can actually group them by labels and annotations. So let's assume you have multiple teams using the same Kubernetes cluster. You can tell them label all your deployments with the same label, and then you'll be able to filter those out. And the last thing is the right sizing. Right sizing actually monitors on the cluster level and on application level the actual consumption versus the requested capacity. So you can see here that the differential is quite tremendous, and you can actually see it on a deployment level. And once you deeper, you can actually see per container. So if I'm going to go into a specific deployment, you're going to be able to see in a graph how much memory is actually being used versus how much memory is being requested, and what is the suggestion that our algorithm behind the scenes gave for this specific container. By that, we can allow customers to optimize their applications that are running on top of the cluster in the most suitable and useful way, making sure that they're not affecting their application performance because they can see the information backwards. And those recommendations are based on up to 14 days, at least 4 days and up to 14 days for you to get a recommendation per specific application. You can also see other things in the Ocean view, but these are the important or features that gives a lot of value to our customers, and I wanted to cover. So thank you for listening for that. I'm going to stop sharing my screen. And we'll pass to the next slide. So we have some time for questions if you guys want to raise any.
There's a great question from Engine in chat that says, when it spins up a new node, does it respect any AZ requirements?
Yes, so we do respect AZ requirements. We take those into account. We actually respect all the built-in Kubernetes node labels. So this would be availability zones, it will be instance types, it would be OS types, and so on. So we can use those. I see another question about, is it fundamental to set pod resources accordingly to take all shown features as advantages, or something like vertical pod autoscaler is used? So whenever you want to use an autoscaler while you're running within Kubernetes, you should specify the requested resources. If you don't specify those, the autoscaler won't know what type of resources or what kind of resources it should accommodate the cluster with. Now, as for the vertical pod autoscaler or the horizontal pod autoscaler, or even KEDA, which is event-based autoscaling features, those are very useful. Those are used for autoscaling on the pod layer. So if you will use those, Ocean will accommodate the infrastructure according to the new pods that will be deployed. But it can also do that for a static environment where you do manually change, like you manually change your deployments or anything like that. So it can work both ways. How does the binding on Spot instances work in the background? I'm not sure I understand this question. If you can try to elaborate a little bit more.
If you were running on Amazon, for example, you would have to have bids for your Spot instances. What does Spot do on your behalf?
Bidding. Okay, sorry, I read binding for some reason. So Amazon changed the entire model of how Spot instances work. They still allow you to bid, but in reality, it's not really being used. So it's quite irrelevant. But we used to take care of that too. And now it's not very relevant anymore. Do these just manifest as node pools in AKS? Okay, so the resources that we allocate for AKS won't be presented in the AKS cluster. You won't be able to see them. In order to see the nodes and the virtual node groups, you'll have to connect to the Ocean cluster.
And I could just share my screen super fast just to show that this actually finished working. And I can go back to my UI and we can see that it's scheduled my changes. It deployed the new cluster, or excuse me, the new application. And in the Spot UI, we can immediately see during my demo, I've actually saved 21 cents out of the 25 that it potentially could have cost, which is pretty cool. My boss will be very happy with this. But in the nodes themselves, we can actually see the utilization. And then we can see that there's the 6 gig. We can see that there's a little less working on this one. And lastly, just to talk about what Amit said, this is my Kubernetes cluster. And here are my node pools. And I'm only seeing the individual node pool itself. I'm not actually seeing anything that's Spot does on my behalf in the background.
You'll be able to see that in the resource group behind the scene, like the resource group that we're using, but it doesn't matter much. There is another question that was that Christian asked. Pulumi, as shown in this presentation, is only a matter of how to set up a cluster and install Ocean product, isn't it? Because cluster nodes are managed by Ocean Spot instances. So the answer is yes. Pulumi is there in order to deploy the infrastructure, the resources. You will use Pulumi in order to upgrade and update those resources too. So the entire life cycle of those resources will be managed by Pulumi. It's an infrastructure as code tool. This is the purpose of it. Paul, you are welcome to add anything if I missed something.
Yeah, so also Pulumi, because it's actually able to interact with Kubernetes clusters that are already in existence. So Pulumi is able to deploy into them pretty easily. And of course, change and not just the deployments themselves, but interact with creating services across the front so that we can actually do it in a HA way. And then, of course, how to hook those services into your DNS provider if you want to swap to a live service. So, yeah. Thank you all so much, folks. I think we're great here. There's a couple of links right here is that you can try Pulumi, pulumi.com/start. Actually, next week, Pulumi are hosting our 2021 Cloud Engineering Summit, which is going to be cool. There's a lot of great speakers involved in that. And thankfully, we have a link right here to sign up and try Spot. I've been playing with it all week in of course, for preparations for this demo. And the things that it's actually taught me are really cool. So I've been talking about it a lot, and I've even been tweeting about it. So I want to say thank you so much for the Spot by NetApp team for having Pulumi involved today, and I've really enjoyed it.
Thanks everyone for listening. It was a pleasure being here today, and Paul, thank you too. It was a pleasure working with you.
Lovely. Thanks so much, folks. Take care.